In the next several lectures, we will look at how scientific theories contribute to the substantive question whether we actually have what it takes to have free will. Now, not all substantive discussion depends on science. That is, you might be able to make some progress on substantive questions about whether we have free will just by doing philosophy. And we've seen some attempts to do this. So in previous lectures, we saw some substantive arguments, like the free will skeptic argues that the idea of free will has inherently inconsistent presuppositions. And so they think that just by thinking about the notion of free will, you can prove that it doesn't exist. So there you're getting a substantive conclusion, there's no such thing as free will, without really doing any science. We also saw that libertarian philosophers argue that we can see that we have free will. We get an argument in favor of the existence of free will just by reflecting on our experience of making decisions. So in those cases, philosophers maintain that we can get to results about whether we have free will or not just by doing some kind of philosophical reflection. But now we'll see that science has also had things to say about the substance of whether or not determinism is true at a minimum, and then by extension maybe whether or not we have free will. So we'll start today with what is at once the most basic but also the most difficult arena, and that is physics. One branch of physics, the branch that deals with the motion of objects, is called mechanics. And questions about the motion of objects, or to use the more technical term, physical bodies, are obviously central to physics. Mechanics was really the first area of physics to be developed in a systematic way. And it applies in lots of different areas. So if you want to know what happens on a pool table, then mechanics is the science for you. Or if you want to know why planets orbit the sun and why moons orbit the planets, again, mechanics is critical to that kind of question, that kind of inquiry. Or if you want to know how molecules bump into each other, again, mechanics is the science that's going to help you answer those kinds of questions. Because in all of these cases, what we're interested in is understanding the motion of physical bodies. So mechanics really provides the basis for understanding those phenomena about the motion of physical objects or physical bodies. That's what mechanics is really about, the motion of physical bodies. Why does the ball move like this? Why do the planets move like that? Mechanics is supposed to answer those questions. There are other branches of physics too, like relativity theory. But for our purposes, mechanics is most important because mechanics is where debates over determinism in physics are engaged. That is, mechanics, the field of mechanics is where we get discussion about whether or not determinism is true. So the other areas of physics, which are really interesting, don't really focus on determinism, and so they're less directly relevant to the problems that we're interested in this course. What we now call classical mechanics is the theory of the motion of physical bodies, that is, it's the mechanics, that was systematically developed by Isaac Newton in the 17th century. We all have some familiarity with this from Newton's three laws of motion. Those laws are at the core of classical mechanics. In classical mechanics, the position of objects was regarded as fixed. This was a fixed feature of the object in the universe. At any given point in time, every physical body, every little object, is in some particular place. And this includes the tiniest particles, like atoms. So, if you recall from high school, the momentum of a body is a really important concept in classical mechanics. And the momentum of a body is the mass of the body times the velocity of the body. And what's really important for us is that momentum is taken to be an intrinsic, fixed feature of every physical body, including the tiniest particles. Traditionally, classical mechanics, this kind of theory of mechanics that we get from Newton, is supposed to be deterministic, that the motion of a particle could, in principle, be deduced from the past and the laws of physics. So, if you knew the positions of all the particles in the universe, as well as the mass and velocity of all the particles, that is, the momentum, along with all the laws of motion, then at least theoretically or in principle, you would be able to predict where every particle would be in the future. We saw this assumption laid out explicitly by Laplace in Lecture 4. And there was great optimism that classical mechanics was pretty much finished, that part of science we could just tuck away, and the rest of it was just mop up. We wouldn't have to do too much more work in the fundamental level of figuring out how mechanics worked. But this optimism about human knowledge of physics was not to last. In the 1920s, a German physicist named Werner Heisenberg argued for a kind of fundamental uncertainty in our knowledge of mechanics, in our knowledge of how physical bodies move. And this was labeled his idea was labeled the uncertainty principle, and it gave rise to a radical new view of mechanics. So the idea that Heisenberg had was that it's not possible to determine simultaneously both the exact position of a particle and its exact momentum. That's the classic instance of the uncertainty principle. Now, perhaps surprisingly, Heisenberg's argument for the uncertainty principle wasn't based on direct experimental demonstrations. Instead, his argument was kind of philosophical. It was based on thought experiments, together with elementary assumptions about the physics and considerations about how the position of an electron would be affected by the light that was required to measure it, for instance, to see it through a microscope. Well, I'll say a little bit more about that in a second, but first I want to observe that even though there was no direct experimental evidence for the uncertainty principle, Heisenberg convinced the generation of physicists of this idea that it's impossible to get simultaneous exact measurements of position and momentum. Since then, there have been ample empirical confirmations that Heisenberg is right, that you can't get both of these things simultaneously. Now, one intuitively pleasing response to the uncertainty principle is what gets called the disturbance theory. And according to this view, what happens is when you measure a particle, that affects what the particle does. So before I said something about shining the light, having the light so that you could see the particle. Well, the idea of the disturbance theory is that if you shine enough light on a particle so that you can see exactly where it is, that light will affect the momentum of the particle. And if you shine sufficiently minimal light so that you don't shine very much light at all to try to get a really precise idea of the momentum of the particle, then you'll be unable to determine the position because the act of measuring affects the particle. Now, it is true that the act of measuring affects the particle. And obviously, since what we're trying to do is measure the particle, figure out where it is and what its momentum is, then this would mean that we never get it all right at the same time. This explanation of the uncertainty principle, or of why we have uncertainty, would allow us to keep pretty much everything in classical mechanics. Now, it is a humbling prospect because it turns out that even on the disturbance theory, it would turn out that we're unreasonably arrogant in assuming that we could know everything about the world, that we could make predictions of everything that would happen. There are some things that are simply beyond humans getting exact knowledge, and the uncertainty principle identifies at least one of these things. But we might pretty easily adjust our minds to accept this, that is, accept the disturbance theory. We could say, well, it's disappointing that there are some things that we can't know. There was a little bit of hubris in the previous centuries about human abilities, but the basic mechanics could still be retained. The fact of uncertainty doesn't seem that bad. It doesn't seem like it's really earth-shattering, even though you might be disappointed that there are limitations on human knowledge. However, disturbance theory is widely rejected now. It doesn't seem to capture the fundamental questions that we want to grasp in basic mechanics. For one thing, it doesn't provide an independently motivated set of predictions about the particles. It doesn't explain why some things are affected by measurement and others aren't. It doesn't predict the particular distributions we actually find for where particles are and what their momentum is. So it looks like a quick fix to the problem of uncertainty, but it turns out that the reasons for uncertainty go much deeper than the disturbance theory would have us think. Instead of the simple, pleasing disturbance theory, the theory that has emerged as the consensus view in physics is also notoriously difficult to understand. This theory that's emerged is called quantum mechanics, and the great physicist Richard Feynman said, quote, "There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe that there was ever such a time," he said. He said, "There might have been a time when only one man did, because he was the only guy who caught on before he wrote his paper. But after people read the paper," Feynman said, "a lot of people understood the theory of relativity." But then he says, on the other hand, he says, and this is a direct quote, "I think I can safely say that nobody understands quantum mechanics." So if one of the greatest physicists of the 20th century claimed that neither he nor anyone else understood quantum mechanics, we will obviously not be able to get to the bottom of things in a half-hour lecture, but we can make some progress. One thing that is already clear is that part of the way that determinism is formulated in terms of predictability is mistaken. We can't make perfect, exact predictions about the position of any given particle that we want to. The uncertainty principle alone shows us that predictability is just not in the cards. But that doesn't show that determinism is false. Notice that on the disturbance theory, it might still be deterministic in the core sense. It's just that we can't get perfect predictability. There are important disputes about quantum mechanics, but let's begin with some claims that aren't in dispute. First of all, quantum mechanics is a predictive theory. Minimally, what it is a mathematical theory that predicts the results of measurements of particles. For instance, it predicts what we will find when we measure the positions of particles. Now, you might have noticed that the way I phrased this is awkward. It's phrased in terms of the results of measurements, what you find when you measure. That seems more removed than necessary. Why didn't I just say that quantum mechanics predicts the positions of particles? I mean, imagine that if you asked a car salesman how far a car would go on a gallon of gas, you expect him to just give you a number, like 30 miles. If you asked how far in a gallon, and he said, the result of a measurement of that distance would be 30 miles, you'd think there was something fishy going on, that he was trying to cheat you or something. So why are the physicists so coy? Why do they phrase the theory in terms of the results of measurements? Well, it's partly because there are deep disputes about how to interpret the measurements, what it means to measure, what happens with measurement, what things are being measured. So to be as neutral as possible, not to bias in favor of one theory or the other, it's good to speak in terms of the results of measurements. Now, one thing that isn't in dispute is that quantum mechanical theory is probabilistic. To explain what that means, we don't need any fancy probability theory. To get the basic idea, it's enough just to think about coin flips and dice. Imagine you had a really big die with 100 sides. If it's a fair die, then for each roll, the chance of hitting, say, 37 is 1 in 100. In other words, the probability of getting a 37 is 1 in 100. We can't predict with any certainty what will happen, at least on an everyday level, but we can make good predictions about the likelihoods that it will come up 37. Relatedly, quantum mechanics makes probabilistic predictions about what you find when you measure particles. So if you have a group of particles, given all the information we can have about the current state of those particles, the theory predicts a range of likelihoods for what we will find when we subsequently measure where the particles are. The theory doesn't make definitive predictions about each particle, and that is, of course, in keeping with the uncertainty principle. The fact that we can't be certain means the best we can do is make probabilistic predictions about what our measurements will show. So just to take one example, if you shoot a bunch of electrons at a screen with 2 slits, quantum mechanics allows you to predict the probability that an electron will hit a certain spot on the back wall. Or put more carefully, it allows you to predict the probability of the result of a measurement of the presence of a particle at a particular location on the wall. A third point of broad consensus is that this theory, quantum mechanics, is enormously successful. It makes extremely accurate predictions. That's consistent with the predictions being probabilistic. The odds makers in Vegas, for instance, are excellent about making predictions about the likelihood that a given team will win a game by how much, and they adjust their payoffs accordingly. That's a probabilistic endeavor, but they do a great job or they'd go out of business. Now, impressive as the bookies are, quantum mechanics does even better. Indeed, some claim that quantum mechanics is the best confirmed theory that we have ever had. Looking across the various experimental tests, it looks like there's a stunning degree of empirical confirmation that the results of the experiments correspond almost exactly to the probabilistic predictions. To give an idea of the degree of accuracy, Feynman offers the following analogy. He says, if you were to measure the distance from Los Angeles to New York to this degree of accuracy, it would be exact to the thickness of a human hair. To summarize where we are at this point, quantum mechanics is a mathematical theory that predicts what we will find when we make our physical measurements. Those predictions are probabilistic, predictions about the likelihood of getting certain results, but the accuracy of these predictions has been amply demonstrated. Now, as described so far, it's overwhelmingly accepted in contemporary science that quantum mechanics is the right view. But what we really want to know is how quantum mechanics impacts the free will debate. And to get there, we need to consider how quantum mechanics gets interpreted. So far, I've just talked about it as a predictive theory, but we might ask, how does it relate to the world? Theories that are predictively successful sometimes admit of different interpretations. Interpretations focus on explaining why the theory's predictions succeed. So consider that you can have a good predictive theory even if you don't know what makes the predictions work. So let's consider a real example. Flatworms exhibit the following pattern of behavior. If you put a bunch of them in a container and block half of the container from light and leave the other half exposed, after a short period, you'll find that most of the worms are in the covered half of the container. And this provides a generalization that extends to further predictions. You can use various kinds of cover, other ways of blocking the light. You get the same effect that the worms tend to be in the covered part or in the unlit part. But you don't yet have an interpretation for why this happens. You just have a predictively adequate theory. Why does it happen? Well, in this case, it's actually pretty interesting because what first comes to mind is you think, well, the worms don't like the light, so they avoid it. But the real answer, that is, the right interpretation of why it happens, is very different. The reason the worms accumulate in the covered half is because they move faster when they're in the light and they turn less often. That explains why they accumulate in this other half, because then they're turning more often and they're not moving as quickly. So that explains why we get the generalization about flatworms converging in the unlit half. Similarly, then, in quantum mechanics, what we know is we have a predictive theory that's really good at predicting what our measurements find. But that doesn't tell you why you find what you find. If you want to know what makes it work, you need to interpret the theory. And so much of the focus in theoretical physics is on interpreting quantum mechanics. Now, there's one really important distinction here. There can be realist interpretations or non-realist interpretations. Realist interpretations maintain that quantum mechanics predicts things well because the theory reflects something about reality, about the nature of the physical universe. Non-realist interpretations avoid any ambitions to describe reality. On these interpretations, you take quantum mechanics as not saying anything about the underlying reality at all, but just about the probabilities concerning the outcomes of measurements. This was actually a prominent approach in 20th century physics. One of the founders of quantum mechanics, Niels Bohr, famously said, "There is no quantum world. There is only an abstract physical description. It is wrong," he said, "to think that the task of physics is to find out how nature is." One could take a similarly agnostic view about the flatworms above. We could describe their behavior, but abstain from theorizing about the underlying natural cause of this behavior. In the case of flatworms, that seems distinctly less satisfying than the explanation that we've actually produced. Now, it may not be that surprising that in quantum mechanics, non-realist interpretation have gradually become less and less prominent. Einstein hated them from the beginning. He thought the whole point of physics was to get at the nature of reality, a nature that's somehow independent of our minds. And he once sarcastically asked a friend whether he really believed that the moon exists only when he looks at it. Moreover, for our purposes, when we're interested in the impact of physics on the free will debate, non-realist interpretations are irrelevant. They make no claims about whether determinism is true or false. And here the quote from Bohr is really telling. He says, if physics isn't supposed to tell us how nature is, then it can hardly tell us whether or not we have free will. So if we're to rely on physics to tell us about free will, we need to focus on realist interpretations of quantum mechanics. What's called the orthodox interpretation of quantum mechanics is not realist, but it can be refigured into a realist theory, and the result of it is a genuinely indeterminist theory of basic physics. So on this approach, the fundamental elements of reality are the quantum states. At a very rough intuitive level, these states are thought of as waves rather than particles. Somewhat less intuitively, but more accurately, a quantum state is a complete mathematical description of a system. Of course, this mathematical description is given in terms of the probabilities of what we'll find when we make our measurements. Now, when measurements are not being taken, the quantum state behaves like a wave, not like a collection of particles, and it behaves in accordance with a deterministic law on this version of this interpretation of quantum mechanics. But when measurements are taken, we do find particles or particle-like behavior. And the particles on this interpretation behave randomly. On this view, there's no determinate position for a particle, but when we make our measurements, the particles jump into a determinate position. And this jump counts as truly indeterminist because of the presumption that, first of all, the system is complete, and second, all of the relevant factors are accounted for. Now, this is a really important part of the theory, because what it's saying is that the particle behaves in ways that are unpredictable given a complete knowledge of the system. And that means that the particle is behaving in a genuinely indeterminist way. There's nothing else. There are no hidden factors. There's nothing we're missing out on that would contribute to us giving a deterministic explanation. This contrasts with the disturbance theory, which allows for the possibility that the behavior of the particle is fully determined, but we just lack access to some of the relevant factors. So on this theory, indeterminism is true of the world. Many, many events are not determined. So this particular interpretation of quantum mechanics maintains that we get indeterminist effects because of measurement. Other theories also embrace indeterminism, but claim that it doesn't depend on measurement. It's somehow a more basic feature of the universe. But for present purposes, what matters is that there are strands of interpretations of quantum mechanics that are expressly indeterministic, that reality at the basic level of particle activity is not determined. Einstein rejected the indeterminism of the orthodox view, famously saying, "I cannot believe that God plays dice with the cosmos." Although people often assume that indeterminism is the only scientifically reputable approach to quantum mechanics, this is not the case. A prominent determinist interpretation was offered by Einstein's colleague, David Bohm. On his view, there are two fundamental features of the universe. As in other accounts of quantum mechanics, there's the quantum mechanical state or wave. But there's also, on Bohm's theory, a set of particles, and those particles always have determinate positions. The system is entirely deterministic, and the reason the laws are probabilistic is because there's certain information that we can't get. There are fundamental limitations on our ability to access information about where the particles are. So the positions of the particles influence what happens, but we can't know the positions of the particles, and as a result, they're sometimes called hidden variables. Although we have limited access, the particles themselves are governed by deterministic laws, and we can use the laws to make extremely accurate, if probabilistic, predictions. So contemporary physics really remains divided on whether determinism is true or not. Both approaches, the deterministic interpretations and the indeterminist ones, are consistent with all of the math and all of the empirical data. But let's consider what the implications might be if one of the indeterminist interpretations is correct. There are no simple implications for free will from this, and there are a variety of different concerns that people have raised. So one concern is that even if there are fundamental indeterminacies, they would never affect big objects because quantum activity happens on the very small scale, like at the level of electrons. So for relatively big objects, the quantum indeterminacies of electrons would just get washed out. And for these purposes, even neurons are big. In fact, they're huge. Now, there are ways to address this worry. Devices that measure quantum activity that are, big macro devices like Geiger counters do show quantum mechanical effects. And if an indeterminist account of quantum mechanics is right, many events like observation might link indeterminist events to macroscopic features of the world. So that's one way of addressing that worry. There's a more serious kind of philosophical worry that even if quantum events are indeterministic, it remains unclear whether this would secure free will. And this is an old problem. It's just like the problem that we saw with the swerve of the Greek atomists. The quantum indeterminacies are random. And a random swerve of an electron in my brain, say makes my brain decide to have the fish. That doesn't seem right for me getting free will, even though my choice might have been affected by the indeterminist element. And the problem is that random activities of electrons don't give me control. Now, this isn't to say that indeterminist physics would refute free will, just that it's not obvious that you can say, well, there's indeterminism at the level of electrons, therefore we have free will. There's a further problem, too. And this is, I think, a really interesting problem. Physics is presumed to give a complete account of the behavior of physical objects, regardless of determinism or indeterminism. In classical mechanics, it's presumed that every physical event is itself caused by a physical event. That is, there's some kind of causal deterministic story to tell. In quantum mechanics, determinism doesn't figure into the theory, but it's presumed still to be a complete theory of physical events. So while it might not be the case that every event is deterministically caused by preceding events, it remains the case that every physical event will follow the laws of quantum mechanics. The physical theory tells the whole story. Nothing other than the physics gets invoked to explain why particles react the way they do. Very few physicists think that they need to look to psychology or biology to understand why particles behave the way that they do. To reinforce this point, consider a simple example. In classical mechanics, if you know where all the particles of a system are and you know all the laws, then you can predict exactly where each particle will be in the subsequent test. So if you shot 100,000 particles through two holes, classical mechanics says that you should be able to predict where each particle will be found. In quantum mechanics, that isn't quite the case. You can't predict where each particle will be found, but you can predict to a high degree of precision the pattern of the particles. You'll be able to predict how many of the 100,000 particles will be in any given location. Since all events behave in accordance with the physical theory, this seems to leave no place for the self to make a distinctive contribution to what happens. It doesn't seem to affect the probabilities. To see this point, consider the following analogy. Let's return to our 100-sided die. If someone says that when you roll the die, there's a leprechaun who sometimes intervenes to make it come up for his favorite numbers. Now, if you roll the die a few times, it will obviously be really hard to refute that kind of vague claim. But let's say you roll it 1,000,000 times, and you find that each of the 100 numbers of your die comes up almost exactly the same number of times at a rate of 1 in 100. If that happens, then this spells trouble for the leprechaun theory. If there was a leprechaun who was intervening to favor a few numbers, the probabilities should turn out skewed. And the worry for free will is that even if there is indeterminism, if the probabilities show up exactly the way physics predicts, then it looks like the self isn't intervening any more than the leprechaun. Whatever the indeterminist processes are, it seems that they're not in my control. Now, some would maintain that quantum mechanics is not complete, that there's more to the story than is offered by the physics, that maybe there are some other objects or entities that contribute to the outcomes. On this kind of theory, some of the indeterminism might come from outside physics. That is, it might diverge from quantum mechanical predictions. And then we might be able to say that the self does intervene in ways that aren't captured by the mathematical equations that we have. Now, there's no evidence for this. There's no evidence that quantum mechanics is not complete. On the contrary, every bit of evidence we have conforms tightly to the predictions of quantum mechanics. So there's no reason right now from the science to think that it's true that the self intervenes, any more than there's reason to think that the leprechaun intervenes in the example of rolling the die. But you might think that it would be difficult to find divergences from the probabilities. And maybe the physicists haven't been studying the right kinds of events to detect divergences from quantum mechanical probabilities. They haven't been looking at things like how electrons behave in our brains. So maybe our choices don't fit within the tight predictions of physics, but the relevant kinds of tests haven't been measured to figure out whether or not this is true. So there may be an additional kind of indeterminacy contributed by the self that's not completely excluded from the physics that we have today. So contemporary physics doesn't provide any decisive evidence in favor of free will. Some prominent accounts actually propose deterministic processes. The standard assumption of physics, though, is that it's complete, and this really poses a more general worry about how even if indeterminism is true, it's not clear that we can credit that to the self. However, I want to end the lecture by emphasizing that the evidence does not rule out the possibility that physics is not complete, and maybe the self does intervene in some way that runs against the probabilistic predictions. The status of that remains unknown.